I'm here today to talk more about clinical AI, not necessarily only my company. And when I say clinical AI, I'm basically talking about a system that can answer questions like find me patients for this clinical trial, what happened to patients on Tagrisso versus Ibrance. It's some sort of an AI that allows you to chat with actual clinical data and drive insights out of it. That's what I mean by clinical AI. I do not mean like how can you bill faster or how can you get more billing data out of Epic. And when we started back in 2017, my co-founder and I, my co-founder is an AI scientist, as I said, my background is medicine. We decided to put a blueprint of what we will do, like what is a clinical AI? And we defined 4 attributes for that. A, it has to be an AI that's capable of clinical reasoning. It can tell when fatigue was a symptom. It can also tell when fatigue was a side effect. And it may sound easy, but it is not. Contextual understanding of clinical data today is like an English speaker reading an English textbook, internal medicine textbook, doesn't essentially understand the nuanced language of medicine. The second is it has to be able to understand the patient journey rather than a document into the patient. So a typical oncology patient has around 1,000 pages of clinical data that has a lot of conflicting facts. The pathologist is saying the patient is stage 4. The oncologist is saying the patient is stage 1. So even if you have a perfect NLP system, you end up with a lot of conflicting information. So how can you reconcile this data across a period of few years of a chronic illness? Third, it cannot hallucinate. And what I mean by that, it's a perfect system, but when it's wrong, it's consistently wrong. When it's right, it's consistently right. We would like to, like in healthcare, you can't tolerate that. You just cannot tolerate the flip of a coin type of experience. And finally, it has to be explainable. If you tell me this patient, like back to my example, Tagrisso had this side effect, I need to see the evidence in the clinical record for something like that, which is not attainable by machine learning only. And for us to do this, we had 2 convictions. Conviction number 1 is LLMs is going to be a commodity. I view LLM as like AWS or GCP, right? Like GCP or AWS is not my company. It just enables me to build my company faster. And I essentially see the same thing with LLMs. There's probably like 200 free ones on Hugging Face today, and I don't see the value of inventing another foundational model. But more, it's about how can you use those models. And the second thing that we had conviction around is the idea of putting specialized knowledge on top of a large language model is essentially like a parrot talking to another parrot. Large language models are probabilistic. The RAG idea is probabilistic on its own. Like trusting that the retrieval model would get the right text to feed your right question is still a lot of probabilities that has to come correctly. So our approach was to couple machine learning or large language models with symbolic AI. And it's funny because when I say symbolic AI, even in an MIT campus, a lot of people ask me, what's symbolic AI? So there is around 2 million papers published around deep learning. In the last 3 years, there's only 20,000 published around symbolic AI. A lot of people think of symbolic AI as rules. If X have like expert systems, and those were one of the reasons why we had the AI winter, so it's not favorably looked at. But that's not what I mean by symbolic AI. That's one part of symbolic AI. But what I mean by symbolic AI is grounding the machine learning into some sort of logic that comes as common sense for a physician. Something like you will never get a headache in your knees. You will never have a patient that is metastatic, but also stage 1. And if you try to do this, the best approach that a lot of people have taken is building a knowledge graph, is building a graph that represents the relationship between different things in medicine. As it turns out, medicine is way more complex than being represented in knowledge graph. The relationship is not binary. If you look at an oncology patient, you have biomarkers, demographics, histology, so many different things that has to be taken in consideration if you really want to have an expert system on top of it. B, medicine is too hard to be just abstracted into rules. The next slide has, the title is a spelling error from my side, which is me hallucinating, but this should be introducing hypergraphs. And the idea of a hypergraph is a more complex system. It understands the layers that would compose a patient, and within each layer has its own knowledge representation within each single layer, and is able to connect those layers together. So imagine you're slicing the patient into histology, genomics, treatments, demographics, and within each single layer, you have your own kind of knowledge representation for it. It also relies on what we call generative ontology. So the problem of, hey, medicine is too complex, we cannot represent it in rules, has been solved with alphabet. Alphabet composes every word that we have ever seen in English or in any language. When you think of the periodic table, every compound comes in from the same elements. So can we abstract medicine into some sort of blocks from which the system can generate ontologies on the fly and scale? So that is essentially what Mendel has been working on, is the idea of building a hypergraph that is built on top of a generative ontology, sits on top of the LLM, and grounds the LLM into reality. After we did that, we weren't able to use it. Traversing a hypergraph is a computationally very challenging problem. It can take like a lot of time. So we had to invent a computational way of traversing it, and I'm happy to present two results and wrap up. One, this graph shows our system, our computational engine, traversing our own hypergraph versus someone running a SQL query on top of a SNOMED type of an ontology. And as you can see, actually, our system is super fast, no matter how much the complexity of the query is. So there's three things that we had to do. Get a generative ontology, build a hypergraph out of it, figure out how you can traverse through that. And the end result is, this is a paper that we just published, and it basically shows if you get 100 clinical trials and you want to query a database of 1,000 patients, and you basically want to find the right patient for the right trial, and you use Hypercube, which is our system, and you use ChatGPT-4, and you use Llama 2. Which system will perform better? Our system performs significantly better, but more importantly, a query that would take 4 hours on a RAG architecture took 12 milliseconds using a Mendel architecture. And more importantly, a query that would have taken around $128 in like API calls would cost around $0.01 using the system, because you're basically querying not a vector database, but you're querying that hypergraph in a computationally efficient way. So that's my talk for today. Thank you so much.